guys, welcome to this video on parametric equations. So let's get straight into it and have a look at what we mean by parametric equations. So let's go to this blackboard here, and essentially what parametric equations are is when you've got a situation where you might be defining the position of a point in terms of another variable. So this here is an example of parametric equations. So notice they come in pairs. So we have one equation that describes the x position and another equation that describes the y position. Now, of course, you could combine these into a single function. So why would you want a pair of functions? Well, perhaps there are situations where you might be wanting the position of, say, an object, so for example maybe a satellite in space, where you don't know exactly what the x and y values would be, but you do know what maybe the time is. So t here could stand for the time. So for a particular point in time, you could plug the time into these equations and then get the x and y values, which would locate maybe the satellite if it was in, say, some sort of elliptical orbit in space. Okay, so that's one example. So we can graph that pretty easily to see what these kind of things look like. So I'm just going to drop back to my desktop here, and we'll bring over Graphmatica here. Okay, and let's remove that particular equation, and let's actually put in that pair of equations that we just had. So with Graphmatica, you basically type in the x and y ones separated by a semicolon, and then we're going to put in some curly braces here what values of t we want to use. So I'm going to go from -3 to +3. Okay, and then press enter. Now you can see here's our function that we've got graphed. Let me just zoom in on that a bit, and as you can see, this is forming a parabola, and because I've only specified -3 to +3, that's why it's stopping where it is. Now I could extend that a bit more to go from -6 to, say, +6. Okay, and then our graph is just extending a bit, so it looks like a parabola but on its side, which is definitely what it is. Okay, so that's one example of a pair of parametric equations. You can have others, like the ones I just had up on the screen a moment ago. Let's take this pair here, and let's actually change some of the values there. Let's actually go with that pair. So this is another pair of parametric equations, and if we clear the screen and then graph this one, you'll see that it forms an elliptical shape. So if some object was, say, at this position here in space, for a particular value of t, we could then find out its location using that pair of parametric equations, which has just disappeared off the screen for a moment. So now we're interested in finding how to derive parametric equations. So how would we do that? Well, we're simply going to make use of the chain rule. So let's actually take this as a specific example, and I'm after dy over dx, the derivative of y with respect to x. Now if I have the parameter t, I could put dy over dt, but then I'd need to multiply it by dt over dx for the left side to equal the right side. So if we've got x equals t squared, I can derive x with respect to t, which would just be 2t, but I want dt over dx, Well, that just looks like the reciprocal of this left-hand side here, and so it is. So it's 1 over 2t. And if we derive y with respect to t, since y is equal to 4t, deriving that, you end up with 4. So putting those two together, using the chain rule up here, we would end up multiplying this here, our dt over dx, and our dy over dt. So those two things there, so 4 times 1 over 2t. We're going to get a common factor of 2 cancelling, so our answer is 2 over t. So notice that with these parametric equations, the solution is in terms of t, even though we are finding dy over dx. Okay, so solutions will be in terms of t. And don't be surprised about that, that's perfectly okay. Okay, let's have a look at maybe a second example. Okay, so let's take x is equal to the square root of t, and y is equal to t squared plus 1. So this is number 310 from your workbook. Right, so let's rewrite our x equation slightly more user-friendly. And let's get dx over dt. It should be a half t to the power of negative a half. And dy over dt would be equal to 2t. Using the chain rule again, dy over dt times dt over dx. Well, dy over dt is 2t. Now, dt over dx, I need to take the reciprocal of that. Well, that's a little bit untidy to do it that way. So let me just see if we can do some work over here. I want to get a tidier fraction, basically. So that t to the power of negative a half, I could put that on the bottom. So the 1 would remain on top, the 2 would be on the bottom, and would have the square root of t. Well, the reciprocal of that is what I need here. So it would be 2 root t over 1. And this is already still over 1, so we end up with 4t times root t. Well, I can combine those powers. That is t to the power of 1 times t to the power of a half, which would be t to the power of 1 and a half, or 3 over 2. And that is the square root of t cubed, with the 2 normally there but not normally written in. So we're going to get 4 root t cubed. It's a little untidy. Let's rewrite that. So 4 root t cubed. That cube's still not looking wonderful, but that's what that is. Okay, so that's how we can get our first derivative. Now, there's also sometimes asked, how do you get the second derivative of parametric equations? So I'm going to see how we can go from our first derivative, which is using this chain rule here. How do we get the second derivative? Well, we're going to use Leibniz's form here. Now, in Leibniz's form, dy over dx is equivalent or is the same as what we're saying is the first derivative. Now Leibniz's form of the second derivative is d squared y over dx squared, and this means the second derivative. So how would I apply that to, say, trying to find the second derivative of parametric equations? Well, d squared y over dx squared, we're going to start with our first derivative, but to get d squared y I need a d here, and I'm going to need to cancel that dt that we're going to have to get in a moment on this right hand side. So dt over dx. Now if you look at that, the dt's cancel, you get d dy, which is d squared y, and dx times itself, so dx squared. So what this means, effectively what we're going to do is we're going to find the derivative of dy over dx with respect to t. Now remember, our first derivative is an equation that's got the t variable on it, so essentially we just derive that again, but then according to this work here we need to then multiply that result by dt over dx, which you would normally get from our first derivative. Okay, so how does this work in practice? Okay, so let's say we had x is equal to 2t squared minus 3, and let's say y was equal to t cubed plus 5. Okay, let's get our first derivative. Okay, so dx over dt would be 4t. dy over dt would be equal to 3t squared. So dy over dx, dy over dt times dt over dx. So dy over dt is 3t squared. dt over dx, the reciprocal of that, so 1 over 4t. Get a little bit of cancellation going on there. We end up with 3t over 4. It was just the t cancelling, not the 4 there. Okay, so here is our first derivative. Let's write that more explicitly. Okay, second derivative. So d squared y over dx squared. Okay, according to this here, and I'm not going to rewrite this, there it is already, we're going to take our first derivative and derive that with respect to t. Well, that's just 3/4 t. Okay, so the derivative of that with respect to t would just be 3/4. Times then dt over dx. Now dt over dx, okay, that's going to be 1 over 4t. So we end up with 3 on top and 16t on the bottom. So this is our second derivative then. So this is a key aspect here, okay, that we need to come back to, and this needs to be memorized. This, by the way, is not on your formula sheet, this second derivative here. So you're going to need to memorize that. Okay guys, we'll catch you in class. Have a good rest of the day.